So welcome to the second part of the lecture on functional calculus. And as already announced in the end of the first part, the topic today is to further enlarge our elementary functional calculus to get more functions in which to plug our operator L. And in particular, we want to also have unbounded functions. And I said, think of the identities, think of z squared, functions where one intuitively knows what happens if you plug in L. And these functions should be included into the functional calculus. And the technique to do it, this is so-called regularization. And yeah, we have to find something new because it is clear we cannot use our way by the Cauchy integral formula to include unbounded functions because the integrals will not converge. So what we will do is we will work with the functional calculus that we have and somehow find a way how coming out of this functional calculus we can enlarge the class. And an important notion for this trick, for this method, is that of a so-called regularizer. So we have a sectorial operator, L on a Hilbert space with sectoriality angle phi L. Pick an angle that is greater than that sectoriality angle. And then we look at the so-called regularizers. So this is a set of functions in our Dunford-Rees class. So for all these functions, we know how to define E of L. And a regularizer is a function where this operator E of L is injective. If you do not see at the moment where this leads to, this is well understood, but we will see in a minute why these injective elements are interesting and important. So these are called regularizers for L. And then I will define the class of functions for which to which we enlarge our calculus. And for this, we first need the notation that with M of S phi, I describe all meromorphic functions on S phi. So not only holomorphic, but also meromorphic functions. And then we take a subclass of this ML of S phi, that is the set of all meromorphic functions on our sector with the property that there exists some regularizer such that E times F comes down to the Dunford-Rees class. So this is the space or set of regularizable functions. So this is those functions which you can multiply by a regularizer and end up in the Dunford-Rees class. And if you have such a function E that is such that E times F is in the Dunford-Rees class, we also will say that this function E regularizes F. So for E to regularize F, you need two things. First, E is a regularizer, so E is in the Dunford-Rees class and E of L is injective. And E times F comes down to the Rees class, Dunford-Rees class. That's the 2 points. Evident first question, if you have this set of regularizers, could it be that it is empty? Which would be bad. Answer no, this cannot happen. The first reason I give you is a rather uninteresting and stupid one, but always the function 1 is in there. So the function 1 is in the Dunford-Rees class, and 1 of L is the identity, and the identity is well injective. Okay, so there is some element in there, but the 1 will not help much because the amount of functions that are meromorphic such that 1 times f is in the Dunford-Rees class, this is more or less the Dunford-Rees class. So this is not a regularizer that will help us to enlarge our class of functions, but it's in there. Okay, so let's look at a little bit more interesting example. And one more interesting example is this resolvent in -1, so 1 plus z to the -1. This is in the Dunford-Rees class because we put it in. Yeah? And what is E of L? E of L is the resolvent of L in -1. -1 is in the resolvent set, so this is an injective operator. So this is also a regularizer, always. And this is a good thing to have. This is one regularizer we will use often. There is another very important regularizer that we will use several times, but which is not always a regularizer. You need one more additional assumption, and that is that the operator L itself is injective. But if L is injective, then there is even a regularizer in the H0 infinity class, and this is the function that we already encountered several times. So z times 1 plus z to the -2. And if L is injective, then I claim that this is then a regularizer. So this is a regularizer for L, as well as these. Why? It's in H0 infinity, so it's surely in Dunford-Rees class. If you plug in L, you get L times squared of the resolvent of L in -1. All these operators are injective. The resolvent is injective, and L is injective by assumption. So this is a product of injective operators. It's injective. Yeah? And this is a very precious regularizer that we will use several times. But make sure, keep in mind, you can only use this one if you know that your operator L is injective. Okay. And second thing, easy but good to keep in mind, is that if you have two regularizers, their product always is a regularizer. Why? Because the Dunford-Rees class is an algebra, so the product of two Dunford-Rees functions is in there again. And if you have two injective operators and you do the product of them, it stays injective. So it's easy to see, but it's a very important feature of regularizers. Okay. So what is now the idea? Why do I talk about regularizers, and how will this help to improve our class of functions where we can put in L? So if you have a function, a regularizable function, so in this class of ML of S phi of regularizable functions, then you can pick a regularizer. And then you know, okay, E is in the Dunford-Rees class, so the operator E of L is well defined and is a bounded linear operator. E being a regularizer means that E times F is in the Dunford-Rees class, so E times F of L is also a nice bounded operator on H. And we know that this operator here, this E of L, is an injective one. So E of L is injective, which means that, you can invert it on its range. So what you get is not a bounded inverse, but you get a closed operator as an inverse, with domain being the range of E of L. So E of L to the -1 as an operator defined on the range of E of L is then a closed operator. And somehow, this is just heuristically, but we should think of this as E to the -1 of L. And then the idea is to say, okay, try the following. We want to define f of L F might be unbounded, F might have poles, F might be awful. Yeah? But we know that if we multiply F by E, we know what to do. So E F of L, this is okay. This is defined in our Dunford-Rees class. Yeah, now take away the E again. It looks like a stupid idea, but it works. Yeah? So you regularize F by E, you get something where you know how to calculate EF of L, and then you take out the E again. So that's the idea. This comes at a price, at a rather natural price, where we want to include unbounded functions like z squared. So f of L in general will not be a bounded operator, so we will have a domain. So, and what is the domain of f of L? It's the set of all functions where this makes sense. So the set of all u in H such that EF of L u, so we have to plug it into this operator. This is an unbounded closed operator, so this has a domain. So EF of LU must be in the domain of this operator, or otherwise stated, it must be in the range of E of L. Okay, that's our try, yeah? To take this domain and this operator, and now let's see if this works. Okay, and this is the first lemma that somehow tells us, okay, this idea is viable, this works out. So what we will check, first thing to check is this idea to define the operator like this. So I will call this star. This gives a nice enough operator, so this gives a closed linear operator in H. Second thing, so somehow this means we've picked the right domain. So with this operation with this domain is a closed thing, so somehow the idea of the domain was not too bad. So then second thing we will prove is to make this a definition, there is some well-definedness issue because we chose this regularizer. Someone else could choose another regularizer. Does this depend on the choice of the regularizer? This would be bad. But I claim it does not. So I claim this definition is independent of the choice of E. Yeah? And third thing we will prove with this lemma is that it's really an extension of the functional calculus that we knew before. So if you start with a function in Dunford-Rees class, what you get out with this proceedings here is the same as f of L. Yeah? So the definition is consistent for functions that are already in the Dunford-Rees class. Okay. So let's prove things, or let's prove at least some of the things, because the first part is already an exercise. So this is something that was done in exercise 1.1, yeah? Where it was shown that if you have something injective, then these inverses get closed operators. Okay. So let's start to show that the definition is independent of the regularizer. So take some function, some regularizable function, and take two regularizers. So E1 and E2, two functions from the Dunford-Rees class that regularize F. And then we have to show that the definition here with E1 or with E2 comes to the same result. And now is of help this part B of the remark that we know if you have two regularizers, then the product is also a regularizer. Yeah? So we immediately know that the product E1, E2 also regularizes F. So, and now the way will be to show that if you take E1 as a regularizer, or if you take E2 as a regularizer, so you will get the same result as if you take the product. So the two must be the same. Okay, so let's start with the product. So what is E1, E2 of L minus 1 applied to E1, E2 f of L? So this is the thing how you would define f of L if you take the product as a regularizer. Okay. So then, here we know that E2f is in the Dunford-Rees class, E1 also is in the Dunford-Rees class. So by the property that our functional calculus on the Rees class is a algebra homomorphism, you can write this as E1, E2 of L to the minus 1, E1 of L, E2f of L. Okay. Now, E1 and E2 are both in the Dunford-Rees class, so you can write this as E1 of L times E2 of L. Yeah? And then the inverse, so this gives you E2 of L inverse times E1 of L inverse. E1 of L inverse cancels this one, so you are left with E2 of L inverse E2f of L. Okay, and you see, if you regularize with the product, you get the same as if you only regularize with E2. And then you do the same calculation with, this is the same as E2 E1 here and E2 E1 here. Yeah? Multiplication in the complex numbers commutative. So you can do the same, and you get that this is the same as E1 of L to the minus 1, E1f of L. Huh? So this is just analogously. Okay. So in fact, this definition is consistent in this sense that it's of no importance which regularizer you take as soon as you have one. And this also makes it really easy to show this consistency in 3, because we can choose the regularizer any way we wish, and the right thing is to choose E equals 1. So this is why it is good to have this regularizer here. If you have a function that is already in the Dunford-Rees class, then 1 regularizes this function, because 1 times f then is in the Dunford-Rees class. And this means that you get the same thing. Okay. So what we have now, we have extended our functional calculus. So let's make this a formal definition. Again, take some angle greater than the sectoriality angle. Take some regularizable function, so in ML of S phi, and then choose the nicest regularizer for f that you find, and define f of L in this way, by this idea star. Okay, and then we've seen this is a well-defined definition, so we know now what is f of L. And this again gives you a functional calculus, so this gives us a map going from the regularizable functions for L into the closed operators in H. And it maps f to f of L. And we will again denote this by phi L. I know this was already the notation for the elementary functional calculus. But as we've seen here, this just extends the elementary functional calculus. So this is a slight abuse of notation, but I hope this is okay. So phi L is again this functional calculus. And this is called functional calculus for our course. In fact, there are many, as I said already last time, many functional calculi. So if you want to distinguish it from another one, this is a so-called sectorial functional calculus. stemming from that it works well for sectorial operators. Okay. And what would be good now, so we know that this functional calculus is consistent with our elementary one, but also already for the elementary one we showed that this is the same as what we get for the Laplace operators by using Fourier transform. In fact, we should do this here again, because we now extended our functional calculus. So the question appears again, is this the same as we get if we look at our functional calculus for the Laplace operator? The answer is yes. And this is a Remark 514, which says please solve exercise 5.6. And exercise 5.6 is exactly that. So the functional calculus for the negative Laplace operator from chapter 4 is consistent on the regularizable functions for the Laplace operator. Whatever that is. So at the moment, for sure, this is one of the feeble points of this extension. We do not really know how big this class is. Because we do not really know how big this class of regularizable functions is at the moment. For sure, it contains the Dunford-Rees class, just by taking the regularizer 1, but the question is, are there more? But we will address this in a while. So we will see it's worth doing it. The class is much bigger, and otherwise we wouldn't do it. But for the moment, it's not that clear. But before we do this, I want to show that we somehow did the right extension, in the sense that as long as it is possible, we still have all the nice algebraic properties of the functional calculus. So the functional calculus was an algebra homomorphism, so it respected, it was linear, it was multiplicative. We cannot in general expect to have this for our operator here, just for the technical reason that it maps into the closed operators, which is even not a vector space. So talking about linearity is already a little bit complicated. But as far as it's possible, we come as close as possible to an algebra homomorphism. So what do I mean by this? Okay, we have again our angle phi. And so the first thing one has to check, and this works out fine, is this space of all regularizable functions for the operator L also is an algebra. So if you have two regularizable functions and you multiply them, you still stay in this class. And we do not really get linearity and multiplicativity because, again, of the old issue of domains. But if you do the right things about the domains, then somehow you get these two things. So for every f and g in the algebra of regularizable functions, and for all scalars lambda, we get that lambda f of L plus g of L is, so the question is, how do these two objects relate? In the Dunford-Rees class, you have equality. Here you do not have equality all the time, but you have an inclusion. So lambda f of L plus g of L is a restriction of the operator lambda f plus g of L. And you have an analog formula for the multiplication. So f of L, g of L is contained in f, g of L. Some heuristics on how to remember which direction you have. What might happen here is that lambda f and g are not so nice functions, making these domains rather small. Let's say lambda f and g both have a pole. And so these operators have small domains. But if the pole, let's say lambda f has a pole at some point and G has a pole, the negative pole at the same point, so these two poles cancel out, so this is a much nicer function. So it might happen that this function, that this operator has a bigger domain. Same here, yeah? So f and g might be nasty in such a way that the product is nicer, but just canceling out some awful things. Yeah? So it might happen that doing the calculation in C first, so doing the multiplication or the sum in C takes away some problems, so the domain gets larger if you do the calculation in C and then plug L instead of first plugging L and then doing the calculations in the operator. That's the heuristics here. Okay, so nevertheless, it's an interesting question. When do we have equality? And one possibility is if G is bounded. If G of L is a bounded operator. If G of L is a bounded operator, then in both cases you have equality. So note, for the first one, this just means one of the two has to be bounded operator, because you can just rename F to be G or the other way around. Here it must be the second one. So if F of L is a bounded operator, you do not know what happens, but if G of L is a bounded operator, then you get equality. Okay. And we can even give a formula for the domain of this product here. The domain of this product is the domain of Fg of L intersected with the domain of G of L. And once we've proved this, you immediately see this yellow equality here, because if G of L is bounded, domain of G of L is just all of H. So this is this domain intersected with H, so you see then the domain of F of L, G of L is the same as the domain of Fg of L. So this second yellow thing will be proved once we've that. And this is a interesting formula that is several times of use, that you really know what comes out as a domain of this one. Okay. So let's prove this. Okay, and the first thing to prove is that these right-hand sides are defined in the first place. Or otherwise, we have to prove that ML of S phi is an algebra. We have to prove that if F and G are regularizable, then the linear combination and the product also are regularizable. And for this, okay, so take two regularizable functions. They both come with regularizers. And I will denote these two regularizers by EF and EG, hoping that everyone understands EF is the regularizer for F and EG is a regularizer for G. Okay, then we immediately get the following stuff. So first thing, again, the product of two regularizers is a regularizer. So the function that we call E, so the product of these two is a regularizer. Second thing, all the regularizers, so EF, EG, and also the functions EF, F, and EGG are done for Riesz functions. That's just the definition of regularizer. And this means that if you take lambda F plus G and multiply with E, so what I claim is this E will be a regularizer for lambda F plus G. So if you multiply lambda F plus G with E, what you get is lambda E G E F F plus E F E G F. So E is E F E G, and if I put it as E F E J E G or as E G E F, this doesn't change anything. Okay, and now you see this function is a sum of two. This is a G. It's a sum of two functions which are products, and this and every factor here is in the Dunford-Rees class. The Dunford-Rees class is an algebra, so this is in the Dunford-Rees class. And this means that lambda f plus g is regularizable by E, so it's a regularizable function. Same thing for the product. So if you take EFG, this is the same as EFF EGG. Both of these are in the Dunford-Rees class, so this is in the Dunford-Rees class, and this means that lambda f plus g and fg are regularizable functions. So what we've proved is that this is an algebra. So it remains to prove these inclusions here, and then the equality if g of L is bounded. So let's first do the inclusions. So let's look at lambda f plus L, lambda f of L plus g of L. Okay, and just put in the definitions. So f is regularizable with EF, so this is lambda EF of L to the minus 1 EF f of L plus EG of L to the minus 1 EGG of L. This is the definition of our extended functional calculus. And now what we would like... no, I want to do it with E. Yeah, I want to do the regularization with E here. No, this is possible because E also regularizes F and G. Because E times F, if you take EFF and multiply with EG, you still are in the Dunford-Rees class. Yeah? So E is also a regularizer for F and G. So in order to calculate these operators, I can choose to take E as a regularizer. Okay, so, and what I want to do next is to factorize out this E of L to the minus 1. But now you have to be cautious because E of L to the minus 1 is not a bounded operator. It's just a closed operator. So factoring this one out comes at the price of an inclusion. This is a subset of E of L to the minus 1 applied to lambda EF of L plus EG of L. Why is it a subset? If you have a function that is in the domain of this operator and that is in the domain of this operator, what does it mean? It does mean it's in the domain of that operator and in the domain of that operator, domain of a sum. Being in both domains means that EF of L and EG of L both are in the range of E of L. But if these two are in the range of E of L, then this, since the range is a vector space, then this sum also is in the domain of E of L. So it's in the domain of this operator. Okay, but you in general you do not get back. Okay, but this inclusion we have. And once we have this inclusion, everything is fine. Because now what is written here is all these functions, EF and EG, they are all the Dunford-Rees class. So in here we can now calculate in our elementary functional calculus. This is now an algebra homomorphism. So this is E of L to the minus 1 lambda EF plus EG of L. And this is the same as E of L to the minus 1 E lambda F plus G of L. And what you have here, just by definition of the extended calculus, is lambda F plus G of L. So this is the first inclusion here. And the second inclusion is the following. You start again with F of L, G of L. Then you write down the definition, and this time I write it down with the EF and EG. So this is EF of L to the minus 1 EF F of L times EG of L to the minus 1 EGG of L. Oh, this is the definition of these two operators. And now the right thing to do is to put in here a do nothing, yeah? So an identity. So you put in here EG of L to the minus 1 EG of L. Now this is an identity on H, so you can put it in without any problems. Then this is both in the Dunford-Rees calculus. So these two commute. So you can take this EG of L over here, and this E of L to the minus 1 EG of L to the minus 1 gives you an E of L to the minus 1. Okay, then there is EF F of L. Times, okay, and then there is this EG of L to the minus 1. This is an identity, but pay attention, they are somehow in the wrong order. No? It's EG of L minus 1, so this is not an identity on H, this is an identity on the domain of EG of L. So this is an identity on the range of EG of L times EGG of L. Okay, and that is the reason why in this case we get the inclusion. So this is now included in if you take here the whole identity. But if you take here the whole identity, what you are left with is E of L to the minus 1, EF F of L, EGG of L. So these two are in the usual Dunford-Rees class, so you can take the multiplicativity of this one, giving you the product of EF, F, EG, and G, which is the product of E, F, and G. So this is E of L to the minus 1, E, F, G of L, and this just by definition is FG of L. And we have the second inclusion. Okay, so what remains to prove is the two yellow things and this equality for the domain of the product. So let's first look at the domain of the sum. So what is left to prove here is that if G of L is a bounded operator, that in fact you really get equality. So let's do this. So if G of L is a bounded thing, then the domain is all of H. So I can do the following thing. So I can start with the domain of F of L and say, okay, that is the same thing as the domain of F of L intersected with the domain of G of L, because this domain of G of L is just the whole space, so I didn't do anything. But now I know what this is. This is the same as the domain of the sum lambda F of L plus G of L. It's just the definition of the domain of a sum of two operators. Sum of two operators has as domain the intersection of the domains. Okay, but now we've seen up here that the domain of this operator is included in the domain of lambda F plus G of L. So this is using this one. This is included in the domain of lambda F plus G of L. Okay, and let's do the same stupid trick again. So this is the domain of lambda F plus G of L intersected with the domain of minus G of L. Because minus G of L is bounded, so this is all of H. But then again, this is intersection of two domains, so this is the same as the domain of the sum. So this is the domain of lambda F plus G of L minus G of L. Yeah, okay, but now you can again use 1. We know that the domain of the sum of the two operators is included in the domain of the sum of L. So again by 1, this is included in the domain of lambda f plus g minus g of L, so of lambda f of g of L, and this is the domain of f of L. Yeah, and now we have done a chain of inclusions, and on the left and on the right we have the same. This is nice. So we've always added stuff and we end up with the same, so everything must be the same. In particular, this set and where's the other one? This set. These two have to be the same. And that is exactly this equality sign here. Okay, what remains to prove is this identity of domains, because if we have that, as I already said, if G of L is bounded, you get the equality here. So what remains to prove is this one. So for the domain of the product, we have the following aim to prove. Aim is to prove this one here. And once we have that, we are done. So we have to prove that these two sets coincide. So let's do this by two inclusions. So firstly, from left to the right. So we start with an element of the domain of f of L, g of L. Okay, so or we start with domain f of L, g of L. So what is this? Just by definition of the domain of a product, this is the set of all u in the domain of G of L, such that G of LU is in the domain of f of L. So in particular, this is a subset of the domain of G of L. This is already nicer because we have to prove that this is subset of this one, so a subset of this intersection, and we have already seen that it is in this one, so we only have to check that it's also contained in this one. So second thing to check, so the domain of f of L, g of L, and this is now exactly what we did here. So this is the part for the product here. What we've shown here is that the domain of f of L, g of L is contained in the domain of f, g of L. So this is just the calculation in 2. Okay, and these two together give the claim. Okay, let's go the other way around. So let's check that every element in this intersection is in the domain of f of L, g of L. So let's take an element in this intersection in the domain of f, g of L intersected with the domain of g of L. And what we have to show is that this element u is in the domain of the product here. So what we have to show is that the domain of the product is all elements in the domain of G of L. Okay, we are in the domain of G of L, that's okay. Such that G of LU is in the domain of f of L. So what we have to prove is that G of LU is in the domain of f of L. That is left to do. And this element G of LU I will call V in what follows. Okay. So what is the domain of f of L? Oh, it should be written somewhere up there. Huh? So what is the domain in our extended functional calculus? It's the set of all W in H such that EFF of L applied to U can be put in the inverse EF to the minus 1, so is in the range of EF of L. Okay, so that's what we have to show. We have to show that this function G of LU is such that if you apply EFF of L, you end up in the range of EF of L. Okay. So, yes? Yeah, you're right. The U should be W because U is taken. So, thank you. Okay, so let's check this. And to do this, I take a small detour. I will look at EG of L, EFF of L applied to this element V. You could ask why. We'll see in 3 minutes. So what is this? We put in what is V, so this is EG of L, EFF of L, G of L, U. Okay. And I do not. Yeah, I do something more. Yeah. Okay. First thing. So these two operators here, they commute. Yeah, this is both in the elementary calculus. So this is EFF of L, EG of L, and now I put G of L. But what is G of L? G of L is. Okay, let's do it in 2 steps. Okay, G of L, U. So this is what is here. So I changed these two, and I put in the definition of V. Now let's put in the definition of G of L. This is EFF of L, EG of L, and then this is EG of L to the minus 1, EGG of L U, by definition of our extended calculus. So you see again, there is EG of L to the minus 1. So yeah, and I know because U is in the domain of L of G that this is in this domain. Yeah? So these two really cancel out. So this is EFF of L, EGG of L U. And this is EFG of L applied to U. Now I know that U is not only in the domain of G, but it's also in the domain of FG of L. So I know that EFG of L is in the range of E of L. This is the definition of being in a domain. Okay, so where were we there? So and this means we know that U is in the domain of FG, so we can also calculate FG of L applied to U. This is okay. And we know that FG of L applied to U is E of L to the minus 1, EFJ of L U. So going back to what we did there, on the left-hand side we had EG of L, ff of LV. And on the right-hand side, we had found this is EFG of LU. So this stuff here is the same as that one. That was the result that we had on what we just had. So this is the same as that. So put this to the other side. This is E of L, FG of L. Or split again E into EF and EG. This is EF of L, EG of L. Note we are now not having inverses. So E is just the product of EF and EG in the Dunford-Rees class, so I can just take them apart by the usual algebra homomorphism in the elementary calculus. So times FG of L. So and then last step, these two commute. So this is EG of L, EF of L, FG of L. And now we've done many calculations, and probably one is lost in knowing where should all this head and why is this good, this calculation. Because what we want to show is that G of LU is in some set. And where's G of LU here? G of LU is this V. But what we have here is an equality. There's a U missing. Have an equality, and both sides start with EG of L. EG of L, EG was a regularizer, so this is an injective map. So we can cancel these two. So if these two elements are the same, these two must have been the same because of injectivity. So EG being injective, this implies that EFF of LV is equal to EF of L, FG of LU. Okay, yeah, what does that help? What is our aim? Our aim is to show that V is in this setup there, so it's in H, and EFF of L applied to V must be in some range. This is EFF of L applied to V. Yeah? So this is the element that we have to show to be where? In the range of EF of L. Yeah. Doesn't matter what this element here is, it's in the range of EF of F. Of EF of L. Huh? So this is in the range of EF of L. Okay, and that is what we had to do. Now it's a involved calculation, and somewhere in the end you sit there and think, oh, it works out. Huh? But we only have to prove that this element is in this range, and this is what's written here. Okay, so this gives us the nice information that our extended functional calculus, okay, it's not an algebra homomorphism, but it cannot, because this image thing of closed operators is not an algebra, but it's close enough. So you have inclusions instead of equalities for your sums and products, but at least you have inclusions, and we also know, okay, if the G of L is a bounded thing, then you really get equalities, even for unbounded operators. So this is nice, and this is somehow the first thing that shows we are on the right track. And then there is now the second question I already talked about. How much have we gained? So how much larger is this class of regularizable functions compared to our Dunford-Rees class? And that's the next thing I want to look at. But before, let's take a small break. So let's continue and see how much we've improved our calculus. And so I put down again here in shorthand writing the result of this theorem 515 that we just had. So the two inclusions and equality if G of L is bounded. And from this we can now get some corollaries. And the first one somehow comes back to the question that I asked in the beginning of this regularization subchapter. What is about functions like Z? Yeah? So is Z of lambda, is Z of L L? And the answer is yes. And we do it a little bit more general. I will show you that for all lambda in C, if you take the function lambda plus Z, that this is a regularizable function, and that if you plug in L, you get what you should get, which is lambda plus L. Okay. This is the claim of this corollary. And the proof is, okay, we first have to make sure that this operator exists. So we have to show that this function lambda plus Z is regularizable. So what we need? We need a function in the Dunford-Rees class, and we need a regularizer, so a function Dunford-Rees class that we can multiply to this function ending up in the Dunford-Rees class. And the easiest choice is to just take the inverse of this one. So okay, let lambda in C and look at F being this function. I will start with this one. So I will first do lambda equal 1, and then we can put the lambda in by some trickery. So let's look at this one. And then how to regularize this one is not that complicated. Take as a regularizer 1 plus Z to the minus 1. And we've seen as an example earlier that this is a regularizer. So this regularizes F. So indeed, we can, at least for lambda being 1, we can now plug in L. And this regularizes F because if you multiply, you get 1, and 1 is in the Dunford-Rees class. So we can calculate what is F of L. F of L is E of L to the minus 1, EF of L. Okay, but EF is 1. So this is just identity. So this is E of L to the minus 1. And E of L to the minus 1, we know what happens. This is a Dunford-Rees class function, so this is 1 plus L to the minus 1 to the minus 1. So this is 1 plus L. Okay. So now we've done it for lambda equal 1, and I said we can do some little trickery to get the lambda in, and just do the following. Write this lambda plus Z as 1 plus Z plus lambda minus 1 times the constant 1 function. And I claim that we can plug in L here, because for this we know it's a regularizable thing. This is a Dunford-Rees class. The operator coming from this one is a bounded thing. So we are in the case that one of the two is bounded, so we even get equality. So this is 1 plus Z of L. So this is now 515 in the equality case, plus lambda minus 1 times the constant 1 function of L. So this gives you 1 plus L by this result, plus lambda minus 1 times the identity. Okay, and this gives you lambda plus L. Okay. So in particular, if you take lambda equals 0, you will find that the function Z applied to L gives you L. And that's because we know about products, also Z squared gives you L squared and so on. Okay, so that's the first corollary. And the second corollary is about domains again. So we take again some phi bigger than the phi sectoriality angle, and let's look at the special case that we have a regularizable function such that f of L is a bounded operator. Yeah, so somehow we know that f of L is bounded. This does not in no way mean that f is in the Dunford-Rees class or something. No? We know that every f of L for f in the Dunford-Rees class is bounded, but there are many, many functions f that such that f of L is bounded, which are not Dunford-Rees. But we have a regularizable function such that f of L is bounded, and I claim that then you have some sort of commutativity. So f of L, L is then contained in L f of L. And we will see that this in particular means that the domain of L is invariant under f of L. So in particular, this means if you plug in elements of the domain of L into f of L, you will again end up in the domain of L. This will rather easily follow from this nearly commutator thing. It's not really commutative because you get an inclusion, but if you pay the inclusion, you can swap the two operators. That's what the corollary says. And the proof is, it's using 515 and 516. So we start with f of L, L. Then we can write this L by 516. We can write this L as the function z applied to L. Okay, now we have both functions here are nice regularizable functions, so we can apply our 515, telling us that if one writes it down correctly, it tells the right thing. So it tells us that we have a product of two f of L, g of L's. This is included in the product of the two functions, and then put in L. So this is z times f, and then put L in the argument. Now we want to commute, and that's why it's a good idea to get this over to the complex numbers side, because on the complex numbers there's no problem in commuting here. So this is f times, I did it wrong way. I already did this. This is okay, and now this is z f of L, and then we can again use this one, but now we are in the nice situation. Usually this wouldn't work because going back would mean the other inclusion, which is bad for the proof, because if we have now this one, this doesn't help. But now the second one is a bounded thing. That is why it's important to suppose that f of L is bounded. F of L is now a bounded function, so now we get bounded operator, so now we get equality z of L f of L, and this is L f of L. So we have the inclusion that is stated here, and now let's see why this property of the domain follows. So people who have worked with commutators of unbounded operators before probably have seen this, but if you have not taken U in the domain of L, what is the domain of L? The domain of L and the domain of f of L, L is the same, because f of L is bounded. The domain of f of L, L is all elements in the domain of L, so thus LU is in the domain of f of L, but domain of f of L is everything. So this is the same thing. Now, use your inclusion. F of L, L is included into L f of L. So this is included in the domain of L f of L. And now this means, now what does this mean? This does mean it's being in this domain means that being in the domain of f of L, but this is nothing, and being such that f of L u being in the domain of L, and that is exactly what we want to show. So we have proved if you have a u in domain of L, then f of L u is also in the domain of L. Okay. So And now let's come to the question, what sort of functions is in our extended Danforth-Riesz class? So what sort of functions do we get by this regularization procedure? And the answer to this question depends heavily on how good a regularizer you get. Whenever you find a regularizer for then you can look how many functions are regularized by this regularizer, and this gives you more information about your regularizable functions. And so at the moment we only have, we have 3. So we have the constant 1 function, which is under no use because it gives no new information. We have the regularizer 1 plus z to the minus 1, which works always. And we have the second regularizer z over 1 plus z squared, which works as long as L is injective. And already these 2 regularizers, so the one that works always and the one that only works for injective L, give us some very interesting information. And some of this I will write down in proposition 518, giving you criteria that so sufficient condition for the function f to fulfill to be regularizable. So the nice thing about these criteria is that you can decide them by just looking at f. You do not have to search for regularizers. You just look at f and you say, okay, this is fulfilled or not. Okay, so take some angle phi bigger than the sectoriality angle. Take some holomorphic function on the sector. So at the moment only holomorphic. And then you can be sure for your function f to be regularizable if, and now there are 2 cases. There is the general case for every L, and there is the better case if you know that L is injective. So let's do first the general case. If you have some constants C, complex constant C, positive real constant S, and the real constant T, such that the following holds. So the supremum for all small z in the sector. So you look at what does the function do in close to 0. So the supremum for the part of the sector that is close to 0 of f of z minus c in modulus divided by z to the s. This is finite. What does that mean? That does mean that your function f in 0 has the limit c. If you let z go to 0, this forces f of z going to c in 0. And even in a velocity of some power of z. So this here is called polynomial limit in 0. So it means your function has a limit in 0. This limit need not be 0. It can be any constant, but it has to have a limit in 0. And this limit must be attained in such a way that if you multiply by some small power of z, it's still the same. By some small power of z minus. So you divide by some small power of z, you still must have this limit. Okay, this is polynomial limit in 0, and you have to know about so this is the general gist. You have to know about what does the function do in 0, and you have to know what does the function do at infinity. And so at 0 it must have a polynomial limit, and in 0 there must be polynomial decay. So the supremum of all z in your sector that are greater than 1 of modulus of f of z divided by z of t, z to the t, this must be finite. So this means there must be some sort of decay at infinity. And this is something you can always achieve, we have a sectorial operator. Whenever you have a function that has a polynomial limit in 0 and has polynomial decay at infinity, this, when it's holomorphic, this function will be regularizable. And the better case, if in addition you know that your operator L is injective, and this we will achieve by using this regularizer 1 plus z to the minus 1. This always works. And if we have that L is injective, then we can use the somehow better regularizer L over 1 plus z squared, and z over 1 plus z squared, and then you get a little bit better result. So if there are real numbers s and t such that somehow you have polynomial control at 0 and at infinity, so this stays the same. Something is weird. Something is weird. Yeah, the polynomial control at infinity is the right thing to put here. You do not need really decay at infinity because the t can be real. But you have it must not grow faster than polynomial. This is what this means. It can grow at infinity, but somehow it must be possible to compensate to this growth of f by some power of z. So this is polynomial control at infinity. What is forbidden is exponential growth or something like that. But as soon as you can somehow, by some polynomial, get the function down to 0, then or bounded, then you have, then this is in the extent. Then this is regularizable. So in general, you need a limit in 0, a polynomial limit in 0, and control at infinity. And if you have the better regularizer, you can generalize, or you get a better thing here. So you also need polynomial control at 0. So the supremum of all z in your sector that are small of z to the s, f of z and modulus must be finite. So this is polynomial control in 0. So this means your function might even blow up at 0, but with some power of z, you must be able to press it down. And you need polynomial control at infinity, so this is the same as above. Supremum of z in the sector modulus of z bigger than 1 of modulus of f of z divided by z to the t. This must be finite. This is polynomial control in infinity. Okay. And for the proof, I already told you what is the idea, so use the regularizers that we know. So let's start with the nicer case, start with B. And as a regularizer, I will take z divided by 1 plus z squared. This is a regularizer because L is injective. And we've seen that once you have a regularizer product, and once you have regularizers, products of regularizers are again of the same quality. So I cannot only take this one, I can even take any power of it. So we take suitable powers of it, and all powers of these functions are regularizers for all k and n. And now this helps us. This helps us to, if the function grows, what do we have to do to regularize? We have to multiply with some regularizer, and in the end get something from the Dunford-Rees class. But if the function has a polynomial growth at infinity or in 0, you just multiply enough powers here to press it down, and then you get something that is even h0 infinity. So in the Dunford-Rees class, that's the idea. So what you have to take is, they have to enlarge the k to make it bigger then both s and t. And then if you look at EF, this is then z to the k 1 plus z to the 2k f of z. And now if you have polynomial control at 0 and infinity, so if you have this one, this gives you s additional power here. So you have k plus s, but s is less than k, so k plus s is still less than 2k. So in infinity, this still goes to 0. And if you are in infinity, this f gives you an additional z to the t, but k plus t is also, it gives you, this doesn't matter. No, this was for infinity what I told. And, if you add infinity, this gives you an additional z to the t up there. So this gives you k plus t divided by 2k. This still goes to 0. If you are in 0, this doesn't help you. But you have f of z divided by z of s. The z to the k is stronger than the z of s. So this still goes to 0. So this is then in H0 infinity of your sector. So in particular, it's in the Dunford-Rees class. So this function is a regularizer. And this was the claim. Okay, and in part A, if the function is only injective, it's not injective, the operator is not injective, then we still have this regularizer. This regularizer you have always. And again, you can take arbitrary powers. So this function 1 over 1 plus z to the k is a regularizer for all k in n. And now again, take your k greater or equal t, and then then you have to look at EF of z and have to show that this is the Dunford-Rees class. Okay, what is EF of z? EF of z is f of z divided by 1 plus z to the k. And now to include this situation with the polynomial limit, just do f of z minus c divided by 1 plus z to the k plus c divided by 1 plus z to the k. So this function here is nice because it's the Dunford-Rees class. Function 1 over 1 plus z is in the Dunford-Rees class. So if you multiply by some constant, then this is okay. So we only have to make sure that this one is in the Dunford-Rees class. And so let's start what happens in infinity. So this you have this polynomial control at infinity. So this function at most grows in infinity like z to the t. The constant doesn't change too much with the growth in infinity. So this function grows as z to the t, but k is more than t. So in infinity, this function goes to 0. What happens in 0? In 0, we know that this difference is less or equal 1 over z to the s. So you get a z to the s here. S is positive. So in 0, this goes to 0. So this is an H infinity 0 function. In particular, it's in the Dunford-Rees class. So this is in the Dunford-Rees class. So we've shown that E regularizes F. Okay, and the nice thing about this criteria is you can just decide it by looking on F. And it shows there are, in particular here, there are many functions that are in the extended Rees class, in our extended Dunford-Rees class, so in the regularizable functions that we did not have before. So polynomial growth in 0 and infinity, there's many functions. Note, for instance, the Dunford-Rees class was contained in H infinity, so every Dunford-Rees function is... no, it was not. Yes, it was. So every Dunford-Rees function is bounded. And here we have many, many unbounded functions. So if you want to have some concrete examples, what did we gain? So for instance, in case A, for every sectorial operator, we can, for instance, now define z to the alpha. And we can do this for all complex exponents which have positive real part. Why? Oh, because this function has a limit at 0. It's 0. And this function has polynomial control at infinity. It doesn't grow faster than some polynomial. Okay, so it's a regularizable thing. Yep. And this function will become very, very important in the next lectures, because what this helps us is we can now, if you plug in L, you can now define L to some power. Okay, L to 2 is not so interesting, but would you have even thought about the fourth root of the Laplace operator? So minus Laplace to 1/4. So somehow, okay, the root of the Laplace operator somehow one derivative, the fourth root of the Laplace operator somehow and half of a derivative. It's possible. You can now define for every sectorial operator that we know, you can define any power with a positive real part. Okay, other examples, and also very important for the following. If you are in case B, I claim that you can, now this is clear, the point is this, that you can treat any bounded holomorphic function. Why? Because you have polynomial control in 0 and at infinity, because they are bounded. So if you apply a little bit S and T, a little bit positive, you immediately have them in there. Okay. So one last thing in this chapter is dealing with functions that are inverse to each other in the complex, so as functions. So the situation is the following. Okay, we have again a sectorial operator. We choose the right sector. Then take some regularizable function. And then take some other meromorphic function on the sector. Such that, so somehow take the inverse, so such that f times g is 1. So you have a regularizable function, and we are interested now what's about 1 over f? If f is regularizable, is then 1 over f also regularizable? You could also ask the question like that, what this proposition is about. So take the inverse of f as a function. So on S phi. And then what I claim is that it's this question whether G is regularizable you can somehow decide this, because this is if and only if the operator f of L is injective. Which somehow is a little bit natural. So because if f times g is 1 and f of L is defined, one would imagine, okay, g of L should be something like the inverse of f of L. And for the inverse to exist, you need injectivity. And it really turns out it's like that. So in this case, if you have injective f of L, then g is regularizable, and then you get that g of L is the inverse of f of L. Okay. Some part of the proof. Okay, so the interesting direction is this one. I know the interesting direction is this one. So if you know that f of L is injective, then you can do the inverse. So because I think I will only be able to do this one because of time issues. So let's do this direction. So let f of L be injective. And we know that E regularizes F. We know that F is regularizable. So take some regularizer and call it E. Then then look at EF of L. EF of L is the same as FE of L. And now, why do I write it the other way around? Because now I know I want to split it into F of L and E of L. And I can only split this with equality if the second operator is bounded and E of L is bounded. So I can split this with equality by 515. So this is F of L, E of L. And now what we know is this is an injective operator. Because E of L is injective as a regularizer and F of L is injective because it was in the supposition. Okay, so this is injective. So this means that EF is itself a regularizer. Because E regularizes F, so EF is in the Dunford-Rees class. And it's injective, so it's a regularizer. And we can now use EF to regularize G. Because what is EFG? EFG is just E, because F times G is 1. Yeah, but E is in the Dunford-Rees class. So G is regularizable. So EF regularizes G. And this means that G is in MLS phi. Okay, so the rest to show that you really get this equality that G of L is F of L to the minus 1. I think this and the other direction I have to refer to the lecture notes. Let me finish by applying this to the obvious example to which it has to be applied, because it's again one way to show that resolvents give you the right result. So resolvent functions give you the resolvents. So take again the right an angle, take some complex number that is not in the sector, and consider the function f being lambda minus z. Okay. We know already what happens. We've shown that this is a regularizable function, and that if you plug in L, you get lambda minus L. Okay. And if you now look at lambda minus z to the minus 1, then we know these two are both regularizable. This was shown in 518. This is a consequence of 518 because they have limits in 0 and they have polynomial control at infinity. And we know from 516 that f of L is lambda minus L. Yeah, and we know that f of L is injective because lambda is in the resolvent set of L. So f of L lambda minus L is injective because this is even boundedly invertible. So this is since lambda in the resolvent set of L. So what 520 tells us is that G of L, so 1 over lambda plus Z of L, is what it should be, is f of L to the minus 1 is lambda minus L, minus L to the minus 1. So it's really the result. So again, we find that we already saw this in the on Monday by doing a completely different way, but we get that 1 over lambda minus z indeed gives you the resolvent functions. Okay. So that's the content of this chapter 5 about functional calculus. And what we will do next is to use this functional calculus to find more stuff about our sectorial operators. I already told you what one thing will be. We will look at fractional powers. So we will take L to some power. And later, well, this is not the next chapter, but then chapters 7, 8, 9, but somewhere there, we will get to looking at the H infinity functions. And the rather natural but interestingly, very delicate and interesting question, when let's say the L is a sectorial injective operator. So I know every holomorphic bounded function is in my calculus. I know for every function done for Dries class, I get a bounded operator f of L. It's not completely stupid to think, okay, it might be that for every bounded holomorphic function, I get a bounded operator. These will turn out to be false, but nevertheless, it's an interesting question, and we will see that for many operators it works. It doesn't work in general, but for many operators it works. And so this will be a later topic then. So the next lectures will continue to work with this functional calculus and to get more properties and to also find properties of our operators via functional calculus. This functional calculus is a tool to get information about our operators. I told you last lecture that somehow the idea is to use this functional calculus as a substitute for what the Fourier transform was the Laplace operator. And to generalize these results that we found for the Laplace operator using Fourier transform to general operators by using functional calculus. So in this sense, this lecture was a toolbox for the next weeks. And thank you for listening and have a nice weekend, and we'll see you on Monday.